Okay. Hey, you guys, are you all there?
Yes.
Yay. Thank you for
We
saying
are.
yes, Cameron.
Yeah.
Thank you. Yeah, I like my internet crashed right when I was trying to get on at like 10:57, or I'm sorry, 11:57. My stupid internet crashed. So I had to turn the modem off and on. Not the modem, I turned the router off and on. I don't know if that helped. Here, just 1 second. I gotta do some stuff. Speaker view. Gallery. We manage participants. Ooh, we have 10 students this morning. Woohoo. Earlier we had like 9 or something. And you guys are aware you can always just unmute yourself whenever you want. I chose not to control that. So if you have any questions or issues, you can always just ask, you know. And ooh, Sumbal just give a thumbs up. Do I get to do that too? Where is that? No, I don't think I get to do a thumbs up, do I? No, not that I can see. No, reactions. Oh, reactions. Ooh, ew, thumbs up. Oh, I'm so happy. Yeah, Rosary, thumbs up, man. Well, I hope this is finding everybody well. Hold on, I'm gonna close my door here. my, my goal for you guys is, again, just to answer any questions we have on homework problems, or if you have any conceptual questions on anything that was taught. Later on, as we approach the exam, I'll start actually giving you guys problems to do, you know, where I'll say, okay, try this problem, try that problem, try this other problem. But for now, I'm just gonna hope that going over homework and answering individual questions is good enough. Who's Calc God? Who is that? I don't know who that is. Manage participants. What's going on here? Am I losing everyone? Wait. Oh, here we go. It is so difficult. This technology is just so stupid. I hate technology. Calc God. Okay, so hey, let's get started. It's 12:05. Are there any questions, any homework problems at all that you want to deal with right now?
Can you go over number 1 on the 5 more electronics problem?
Yeah, sure. Let me get that actual sheet of paper, that document. Here, I'm going to do the share screen thing with my iPad. Share. Okay. Wait. Okay. Uh, okay, great. And here, just 1 second. All right. So then I'll just put it right here. All right. And so Cameron, this
Yeah.
is problem. You say problem number 1.
Yes.
Okay. Hold just a second. You have one? Oh, okay. Number 1, you've got a 6-volt battery supply, and you've got 3 resistors, a 3 ohm, a 20 ohm, and a 30 ohm attached. And so the way you do this is, number 1, get the equivalent resistance of the circuit, and then number 2, get the current out of the battery, and then number 3, answer whatever crazy questions they have. Okay, and I think I'll do the problem just right here. So actually, I have this in recall. I've already scanned this in. So looking at number 1, are you okay that the equivalent resistance, I've got a 20 and a 30 in parallel with each other. I know
Mm-hmm.
they're in parallel because the left hand of the 20 is holding the right hand of the 30, and the left hand of the 30 is holding the right hand of the 20. So they're in parallel. They have the same voltage across them. Whatever voltage drop the 20 has, the 30 has the same voltage drop. So
Okay.
this equivalent resistance is going to be the 20 ohms in parallel with the 30 ohms. Once I get that equivalent resistance, that's going to be in series with the 3 ohm resistor. Because whatever current enters and exits the 3 ohm resistor must enter and exit this parallel resistance.
Mm-hmm.
And so the 3 ohm is in series with this 20 and the 30. So I'm going to add 3 ohms to that. So now let's go ahead and do my calculator. I'm going to do 1 over 20 plus 1 over 30, and then get the inverse of that. And that got me 12. And then I add that to 3, and that gets me 15 ohms. So are you okay that the equivalent resistance of this circuit, the resistance that the battery sees, is 15 ohms?
Yeah.
Which means the current coming out of the battery is going to be 6 volts divided by 15 ohms. And 6 volts divided by 15 ohms is 0.4 amps. So now I know that I'm getting 0.4 amps going into, so that A1, the ammeter that's sitting there, is going to detect 0.4 amps. Because I have 0.4 amps going through 3 ohms, that means the voltage drop by Ohm's law is going to be 0.4 times 3, which is 1.2 volts. So I have a 1.2 volt voltage drop across the 3 ohm, which means V1 is going to show 1.2 volts. Finally, because the voltage here is 6 volts, and then I'm losing 1.2 volts here, that is my, every coulomb of charge has 6 joules of energy here, and then it loses 1.2 joules of energy, every coulomb of charge, so that every coulomb of charge at this point will hit this node with 4.8 joules of energy, which means the voltage here is 4.8 volts. That means that the voltage drop across this 20 ohm resistor is 4.8 volts, because the voltage at the negative terminal of the battery is 0. So now I'll just do 4.8 divided by 20. That's Ohm's law. And I get 0.24 amps. So I have 0.24 amps going through this 20 ohm resistor. I have 0.4 amps hitting this node. It's like a river with 0.4 amps. Then part of the river goes down and the rest of the river keeps going through the 30 ohm. So since I had 0.4 amps approaching this node and 0.24 amps turning right, then the remaining 0.16 amps has to go through that 30 ohm resistor. And then finally 0.16 times 30 is 4.8, which is what I would expect, because this here is 0 volts and the voltage here is 4.8 volts. So I'd expect this voltage drop 0.16 times 30 to be 4.8, and it is. So it's a 4.8 drop. So Cameron, do you have any question or issue on that?
No, I think you covered it. Thank you.
Okay. Yeah. And so you'll notice in my doing this, I'm doing a lot of talking because I want you to see my logic, how I recognize that the 20 and 30 were parallel, how I recognize that the 3 was in series with that parallel resistance.
Mm-hmm.
That's all making sense. Hey, and does anyone have any other questions or issues? I'll answer or show you as much as you want.
Could you do number 73 on the homework?
Number 73 on the homework? Yes, Jacob. 73. This is an internal resistance problem. So let's go ahead and do this. Okay. Oh, here, just a second. I gotta write something. Hello. Okay, great. So a battery, up till now, we've always drawn a battery like this. And we just say, okay, here's my battery. You know, here's the positive terminal, there's the negative terminal. But actually, every battery consists of both a battery and an internal resistance. But this internal resistance isn't some discrete thing that you can like cut open a battery and remove. This internal resistance is inherent to the battery. it's innate to the battery. You know, it's in the warp and woof of the battery. I don't know how else to say it. So this dashed rectangle, this is the battery. And so this is actually the positive terminal of the actual battery, and this is the negative terminal of the actual battery, a battery that consists of both a voltage source and an internal resistance, which I'll call R sub I. This is number 73 that you're asking me about, Jacob. And 73, they actually come right out and tell me the internal resistance is 0.5 ohms. So the internal resistance of this battery is 0.5 ohms. They don't tell me what the voltage of the battery is, but they do tell me that the terminal voltage is 1/2 of it, which means 1/2 of the voltage is being dissipated across the internal resistance, and then the other half of the voltage is being dissipated across all of these parallel resistors, which we don't know how many there are, you know. But each one of these parallel resistances is 15 ohms. So Jacob, before I haul off and start telling you like my way of doing it, oh wait, did this just turn off? Stupid thing. Okay. How did you think of it? Like, how did you try to approach this problem?
Oh, I didn't visualize it the right way. I thought like when it said 1/2, I thought it was 1/2 like across the whole entire circuit. And so I think that's where I messed up.
Okay, well, actually, it kind of is. I mean, you know, the voltage here is 1/2 volts, and the voltage here is 0 volts. So actually, across the entire circuit, if you mean circuit, you mean like these guys, the resistor. Then yeah. Just 1 second. My screen share has stopped working. Let me see if I can get it back. My God. This is like just madness. Okay, here we go. I'm going to stop mirroring, and then I'm going to start mirroring and see if it works again. Okay, great. The technology. Okay, just a second. All right, let me have this go down. Oh, no, it is down all the way. Huh? Oh, there you go. Or do I have it on the wrong side? No, I got it on the right side. Oh, stupid thing. Alrighty. So you see that okay, correct?
Yeah.
Okay, that's the circuit. So okay, so you didn't picture it looking like this?
Well, I had the parallel resistors, but I thought when it said 1/2 of the voltage, I thought it meant like you're still left with 1/2, and I was like confused about that. And I was like, oh, but then I think I see what it is now.
Okay.
I didn't know it was asking that it was 1/2 after the internal resistor of the battery.
Oh.
Yeah.
Okay, great. And you know, since it's 1/2 after the internal resistor, that means the voltage drop across the internal resistor must be 1/2 of the voltage as well. Well,
Okay.
I'm going to teach you later about voltage dividers and current dividers. So the quick way to think of this is, if you're cutting that voltage in half, then the equivalent resistance of all these parallel resistors has to be equal to that resistance.
Yeah.
Because both the internal resistor and all of the parallel resistors together are getting the same current. And so, here, let me make sure focus is back. It's lost its focus. Wow, stupid thing. Here's a second. Okay, there we go. And now am I going to get it back? No. Okay, there we go. And so because the internal resistor and the equivalent parallel resistances all have to have the same current going through them, they must have the same resistance in order to have the same voltage drop. So to complete this problem, this internal resistance, which is 0.5 ohms, has to be equal to the equivalent resistance of all of those parallel resistors. And when you have n parallel resistors in parallel, then the equivalent resistance ends up being each resistance divided by N. That is, in this case, it'd be 15 ohms over N. So I need 15 ohms over N to equal the same as the internal resistance. And so N ends up being 30.
Okay,
So
that
if
makes
I
sense.
have 30 parallel resistors, 30 identical parallel resistors, their equivalent resistance of 15 ohms, their equivalent resistance will be a half ohm, which is exactly the same as the internal resistance of the battery. And so since both those resistances get the same current, they'll both have the same voltage drop, so they'll each get half the voltage.
Okay, thank you.
You're welcome. Yeah, they asked about that during the 10 o'clock session as well. So it's a pretty sophisticated problem, I think. Hey, any other questions or issues?
Oh, in general, can you explain why the voltmeter, it measures the voltage drop rather than like the actual like
Oh, good. Yeah. See, here's the thing. It's like when here, let me just do this. Let's say you've got some conductor, all right, and the conductor has a bunch of charge going through it, right? And this charge has each coulomb of charge has a particular amount of energy. We'll give it a voltage, okay? And so each charge has a particular amount of energy. But the thing is that energy is always relative. The energy of the charge is relative to what the energy of the charge somewhere else is. So for example, if we said all of this charge had 12 joules per coulomb of energy or electric potential, and then when we get to here, all of this charge has 5 joules per coulomb, which means somewhere it gave up every coulomb of charge gave up 7 joules of energy, then I would say that the voltage drop from there to there is 7 volts. And that's all a voltmeter can measure. A voltmeter, unless I actually stick the black lead of my voltmeter, here's my voltmeter. Unless I actually stick the black lead of my voltmeter into the ground, where, oh shoot, yeah, let me do this. Unless I stick the black lead of the voltmeter into the ground, where now the black lead is literally measuring 0 volts because we designate earth ground as being 0 volts, you know, unless I do that, my voltmeter isn't going to measure absolute voltage. It's only measuring relative volts. So if I put my voltmeter here and I put the black lead to the 5 volt place and the red lead to the 12 volt place, then my voltmeter is going to measure 7 volts, because all a voltmeter can measure is the difference between what the black and the red lead measure.
oh, okay. Cool.
So yeah, you're
Thank
just
you.
all a voltmeter can measure is the voltage drop, the voltage difference between two places on a conductor. But if my black was attached to the earth, if I stuck it into some wet ground, then I could be confident I'm measuring, true voltage.
Oh, okay.
But now the weird thing is, of course, we're designating Earth, planet Earth, as being 0 volts. But compared to Mars, who knows? Maybe planet Earth has some voltage compared to Mars, in which case we're just measuring all of our voltages compared to Earth because we're designating Earth as 0 volts. But if Mars is 0 volts, then all of our voltages are off by a little bit, if it's absolute voltage we're trying to measure. So if I can just end this with one last thing, you're never measuring absolute voltage. Whenever you measure voltage, it's always just voltage relative from one place to another.
Cool.
So is that good
Thank
for you,
you.
Cameron?
Yeah.
Yay. Okay, good. Hey, any other questions or issues? Any other problems you want to see? Don't be shy.
Can you do number 74 on the homework?
Is that Rosary?
Yeah.
Yay, number 74, here it comes. Let me get my sheet of paper. No, number 74. So it says where is number 74? Oh, there it is. So it says 1.4. Here, let me shove this over a little bit. Okay. I tell you, this is madness. Why I can never get it to focus. Here's a second. I guess maybe because the paper's white or something, it doesn't like that. Well, maybe if I write some more, it'll focus. A 1.4 ohm resistor is connected across a 9-volt battery. The voltage between the terminals of the battery is 8.3 volts. Find the internal resistance of the battery. This is the type of problem I'm definitely going to give you on the exam. And step 1 is to draw the battery. And I want to remind you, a battery always consists actually of a voltage source and an internal resistance. So this thing in the dotted rectangle, that's my battery, alrighty? And we don't know what the internal resistance is. However, they tell me that this is a 9-volt battery. So the voltage of the battery is 9 volts. Then we attach a 1.4 ohm resistor across the battery, 1.4 ohms. And they tell me that the voltage is 8.3 volts. That is the terminal voltage. The voltage we see across the terminals is 8.3 volts. And remember, we always designate the negative terminal of the battery to be 0 volts. And I also want to remind you that with a conductor, we assume an ideal conductor. So whatever the voltage is right here, it'll be the same voltage everywhere on a conductor. So that means if the terminal voltage is 8.3, that means there's also an 8.3 volt drop across my 1.4 ohm resistor. So here's the technique. Here's the process you have to go through. Number 1, get the current. We're going to get the current out of the battery. And you'll notice this is a 1.4 ohm resistor with an 8.3 volt drop across it. And so the current is going to be 8.3 volts divided by 1.4 ohms. That is, the current is going to be 8.3 divided by 1.4. So I get 5.9 amps. So that's the current coming out of the battery. So my battery is delivering 5.9 amps. Okay. In addition, the next thing is to get the voltage drop across the internal resistance. And because this is a 9-volt battery, but the terminal voltage is 8.3 volts, that tells me that I must have a 0.7 volt drop across that internal resistance for the voltage to fall from 9 volts. Right here, it's 9 volts. For the voltage to fall from 9 volts to 8.3 volts means there's a 0.7 volt drop. So it's 9 volts minus 8.3 volts, which is 0.7 volts. So now I've got the current going through the internal resistance. I've got the voltage drop across the internal resistance, which means, again, using Ohm's law, I can get the internal resistance. So my internal resistance is going to be the voltage drop across the internal resistance divided by the current, which is 0.7 volts divided by 5.9 amps. So 0.7 divided by 5.9. And I end up with 0.12 ohms. And so that's the internal resistance, 0.12 ohms. So Rosary, I know I went through it really quick. Any question or issue?
No, that's fine. I just wanted to see how you did it because I didn't get the right answer.
Okay, good. Yeah, that's what you do. Just put it all together. Get the current, get the voltage across the internal resistor, and then do Ohm's law.
Yep, thank you.
You're welcome. Hey, any other questions or issues?
I have a question about number 2 on the electronics worksheet.
Okay.
Is the current across the 20 ohms the 0.167 amps?
Here, just 1 second. So we're looking at number 2.
Mm-hmm.
Wait for my internet to catch up. Okay, so is this Jada?
Yes.
Okay. Yeah, my little thing isn't showing you. I don't know why it's not. Oh wait, maybe I've no, that didn't work. Well, here he goes. Now it just showed Jada. This is just, none of this makes any sense at all. Right? Oh, there we go. There's Jada. But it doesn't let me scroll. Stupid thing. Alrighty, well, whatever. Okay, so Jada, I'm sorry. I'm just still playing with Zoom. So what was your question?
Is the current across the 20 ohm the same as the current across the 14 ohm?
No. And also current doesn't go across things, it goes through them. Think of it as water going through a hose. And whatever current is going through that 14 ohm resistor, once it hits the node where the current goes through the 14 ohm resistor and then hits this node, at that point the current splits into two tributaries. One part of the current goes through the 30 ohm and the other part of the current goes through the 20 ohm. And so no, the 14 ohm and the 20 ohm aren't getting the same current.
Okay, thank you.
You're welcome. Yeah, and your strategy for doing number 2 is the same as number 1. Step 1, get the equivalent resistance of the entire circuit. And I'll actually just show that really quick. The equivalent resistance of the entire circuit, you've got the 20 and the 30 in parallel with each other. You got the 20 and 30 in parallel with each other. And then, oh wait, oh shoot, stupid thing. And there's my cat Lucky, who actually passed away. So you've got the 20 and 30 in parallel, and then once you get that equivalent resistance, the 14 and the 10 are in series with the equivalent resistance of the 20 and the 30. That is, whatever current enters and exits the 14 enters and exits this entire thing, and then enters and exits the 10. So it ends up being plus 10 plus 14. So that ends up being what, 10, 24, 36, and then you do the rest of the problem just by doing Ohm's law for everywhere. But that's the equivalent resistance right there.
Okay, thank you.
You're welcome, Jada. Hey, anything else? I'll answer any and all questions.
Can you please go over number 75?
Sure, Sumbo. Let's look at it.
Mhm.
Number 75. Okay, let me get this over here. So here's number 75. You know, it's interesting. That's actually a problem they asked about in the 10 o'clock session as well. When a light bulb is connected across the terminals of the battery delivers 24 watts of power to the bulb, and a voltage of 11.8 exists between the terminals of the battery. Well, and then they want to know what the internal resistance, they give us the internal resistance of the battery. What's the EMF of the battery? Well, hey, step 1, you have to make a drawing. So here I'm going to draw my battery. And now that we've learned about the internal resistance of a battery, we're going to draw our batteries, including the internal resistance and the voltage. And interestingly enough, on the AP exam, if this were to be on the AP exam, which it won't because they're not going to cover it, but if it was on the AP exam, I would say do not make a drawing like this unless they're specifically talking about the internal resistance of the battery. You know, if they're not asking about internal resistance of the battery, then just draw your battery like this and go on your merry way, you know. But if they're specifically asking about internal resistance, then you're going to have to make that drawing. Well, they don't tell me what this resistance is, but they do tell me that it's dissipating 24 volts. And then finally, they tell me that the terminal voltage of the battery is 11.8 volts. And of course, the negative terminal will be 0 volts. Okay, so, oops, I lost my focus. Here, maybe that'll get, yeah, that got it back. Great. So, because this is a perfect conductor, if it's 11.8 at the terminal, it's 11.8 there, and it's 0 volts there. So, Sumbal, first of all, did you get, and the internal resistance, they actually give us the value of it. It's 0.1 ohms. And they want to know what the voltage of the battery is, what the voltage would be if you had like an incredibly large resistor across it. If you had a huge resistor here, then very little current would leave the battery, which means there'd be very little voltage drop across the internal resistance, and the terminal voltage would be pretty much what the voltage of the battery itself is. But in this case, this is probably a very, very small resistor so that you're pulling a lot of current so that you're getting a significant voltage drop across that internal resistance. Okay, so Sunbal, what did you do at this? First of all, did you successfully make this drawing?
Yes, I did.
Okay, and then what did you do?
Then I had found the current using P equals IV.
Oh, you're so smart. Now, what did you, okay, beautiful. Hold on, I'm gonna cough. Great, I'm just gonna do it. I'm just gonna do it your way. I actually did it a different way, but you know what? Your way is fine. It's all good. So here's 24 watts has to equal I times 11.8 volts. Okay, so you got the current as being 24 divided by 11.8. So you got the current being approximately 2.0 amps, right?
Yes.
Okay, yay. And so here I'm kind of messing up my writing because my hand is scrunched. Oh, well, that didn't help at all. Okay, so now that you know that the current is 2.0 amps, you know what this resistance is 0.1 ohms. So you got 2 amps going through it. So are you okay that the voltage drop across this 0.1 ohm resistance must be 0.2 volts?
Oh, okay.
And so since that's 0 volts, that's 11.8, and you've lost 0.2 volts getting from here to here, that must mean the voltage right here is 12 volts. So that means it's a 12-volt battery.
Okay, thank you.
You're welcome. Does anyone have any question or issue on this or anything else?
I know you said for the 5 more electronics problems, number 2 should be like number 1, but I'm actually really stuck for some reason.
Like it's not
Same.
happening for you on number 2?
Yeah, it's just not working out.
Well, first of all, did you successfully get that the equivalent resistance is equal to 36 ohms?
Yep.
Okay, good. And since this is a 6-volt battery who feels 36 ohms across his terminal, did you get that the voltage, the current out of the battery is 1/6 of an amp?
Yep.
Good. And then let me ask you this incredibly key question. If the current out of the battery is 1/6 of an amp, what must be the current into the battery?
Isn't it also 1/6?
Yes, sir. Also, it's just like a hose. Whatever water enters the hose has to exit the hose. Whatever water exits the hose must enter the hose, you know? So yeah, if you've got
Yeah.
the positive terminal putting out 1/6 of an amp, then you must have 1/6 of an amp entering the negative terminal because the charge isn't gained or lost. It's not like there's a place where a bunch of my current is flying away, like having a leak in your hose. So yeah, if 1/6 of an amp is exiting the battery, then 1/6 of an amp has to be into the battery. So now we can actually get our voltage drops, right? This voltage drop
Yeah.
here is going to be 7/3 of a volt. That is 1/6 of an amp times 14 ohms. So that's 7/3 of a volt. So if the voltage here is 6 volts, the voltage at the positive terminal of the battery is 6 volts, then you lose 7/3 of a volt. Your charge is giving up 2 1/3 joules of energy. Every coulomb of charge is giving up 2 1/3 joules of energy. So that means that the voltage right here must be 3 2/3 volts.
Okay.
Because you gave up 2 1/3 volts passing through here. Similarly, I've got 1/6 of an amp passing through this 10 ohm resistor, which means I'm going to have a voltage drop of 5/3 of a volt. This current as it passes through this 10 ohm resistor is giving up 5/3 of a joule of energy, 2 2/3. And so since the voltage here is 0 volts and the voltage here is 0 volts, then the voltage here must be 1 1/3 volts. No, 1 2/3 volts. 1 2/3 volts, because that's how much you're giving up. So now do you see why the voltage V2 must be 2 volts? Because the voltage
Why
here is
V2
3
must be 2?
2/3, and that's the red lead of your voltmeter. and the voltage here is 1 2/3. That's the black lead of your voltmeter. So
Oh,
that must mean the voltage V2 is 2 volts.
all right. Yeah, that
And
makes sense.
yeah, and since it's 2 volts, that means, and you've got 20 ohms here, 2 volt drop, 20 ohm resistor. That means of the 0.16666 amps that are exiting the battery, 0.1 amps is going through the 20 ohm resistor, and the remaining 0.0666666 amps is going through the 30 ohm resistor.
Wait, how did you split it like that? Why does that work like that?
What it looks like is, again, I used Ohm's law. I know that this
Uh-huh.
voltage drop here is 2 volts.
Yeah.
I know this voltage drop is 2 volts because that's 3 2/3 and this is 1 2/3. So since the voltage drop is 2 volts and this is a 20 ohm resistor, that must mean by Ohm's law that 0.1 amps.
Yeah, I see it now.
Okay. So
All right.
0.1 amps is going through the 20 ohm resistor, which leaves 0.066666 amps to go through the 30 ohm resistor because we got 0.16666 exiting the battery.
Mm-hmm. Okay, thank you.
You're welcome. Yeah, and these problems, I'll tell you, the only way to get good at them is to do them. But after a while, you get extremely good at them, and it's fun. You just go, hey, this is easy.
Is it possible to find the current of the 20 ohm and the 30 ohm using proportions of like the 0.166? Or is that what you were talking
No,
about?
yes, absolutely. Yeah, that, current seeks the path of least resistance. So, the 20 ohm is going to get more current than the 30 ohm. It's like
Okay.
your current is traveling down this river, this wire, and then it reaches this node, and then it has to decide how much of me goes this way and how much of me goes that way. And whatever the lower resistance path is, the lion's share of the current will go through that path. And then, Cameron, when I teach the lesson on voltage dividers and current dividers, at that point you'll learn that the 20 ohm gets 3/5 of the current and the 30 ohm gets 2/5 of the current.
Oh, okay, cool. Thank you.
You're welcome.
Mr. Shainer, so on
Yes.
problems like these, would you stay away from making them decimals because then
Oh.
you lose some of the value?
No, you can make them decimals. I just chose fractions
Okay.
because I'm doing this screen share thing, and I had to make sure that I was using as little ink as possible. I didn't want to clutter my drawing, so that's why I chose fractions instead of decimals.
Gotcha.
Yeah. Is this working? Oh, this thing. When my iPad goes on auto, turn off or whatever, then I lose this. I have to redo this here just a second. Yeah, Ron.
Do we have the red pepper? The little red canister? Are we out of that too? Pepper?
Oh,
The red and white canister?
no, unless you used it all in your last red, like cayenne pepper.
No, pepper. Regular pepper. And the red and.
Oh no, we're out of that. Oh, black
So we
pepper,
have no.
ground black pepper. Yeah, that's why we're hoping that Vaughn's comes through for us because I think
Okay,
you ordered
we
it.
that.
Yeah, we have no ground pepper or other no black pepper at all.
Mr.
That's
Shainer, one
weird.
more question.
Yes, Andrew.
How did you get 5/3 volts over the 10 ohm resistor?
Because I know that 1/6 of an amp is passing through the 10 ohm resistor. And so since 1/6 of an amp is passing through the 10 ohm resistor,
Oh, it's
1/6
just
times
basic
10 is,
multiplication.
yeah, I did Ohm's law.
Okay. All right, thanks.
That's really lagging now. There it is. When I was talking about it, I was pointing to it, but then 10 seconds later. Hey, any other questions or issues?
On the same page, can you go over part C for number 4?
Sure. Yeah, this is an important Xerox in my opinion. Here, I've got for some reason my my mirroring hasn't done the thing yet. Wait a second. Okay, all right, now it's working. Stupid thing. Stupid technology. There you go. So we're looking at number 4. And number 4 is asking, find the current out of the battery, the total power consumption of the circuit, and the current through the 20 ohm resistor. Okay, and so I'm gonna do just as always, number 1, for these types of problems, number 1 is to get the equivalent resistance of the circuit. And looking at the circuit, do you see that the two 30s are in series? Because whatever current enters and exits one 30 has to enter and exit the other 30. So I've got 30 ohms plus 30 ohms, alrighty. But those two resistors in series are in parallel with the 20. That is, the left hand of the 20 is holding the right hand of the two 30s, and the right hand of the 20 is holding the left hand of the two 30s. So those two 30s are in parallel with that 20, and then that entire resistance is in series with the 50, because whatever current enters and exits the 50 has to enter and exit all of this stuff. And so I'm going to add 50. Alrighty, so my equivalent resistance, 30 plus 30 is 60. 60 in parallel with 20 is 15, if I'm not mistaken. But I'm gonna do it right now. Yeah, so 60 in parallel with 20 is 15, and then 15 plus 60 makes 65. So the equivalent resistance of the circuit is 65. So step 2, we need to find the current out of the battery. And the current out of the battery is going to be V equals IR. So I got 13 volts over 65 ohms. Of course, that's why I chose 13 volts. And that ends up being 0.2 amps. Yeah, and once I get the 0.2 amps, and this is, Cameron, is this you asking about this?
Yeah.
Okay, then are you okay that now that I found the current coming out of the battery, I can answer pretty much any question they ask by doing Sudoku, or Sudoku. Yeah, and where I've got 0.2 amps going through a 50 ohm resistor, so that's a 10 volt drop across that 50 ohm resistor. So my current starts with 13 joules for every coulomb, but it loses 10 joules per coulomb in going through that 50 ohm resistor. So now we're just stuck with 3 volts. And since the voltage here is 0 volts, do you see that I have a 3 volt drop across that 20 ohm resistor?
Yeah.
And so 3 divided by 20 is 0.15, and that's the current going through the 20. So 0.15 amps goes through the 20, and the remaining 0.05 amps goes through the 60.
Okay, thank you.
And you're welcome. And to address your last question about current dividers, yes, since 20 has the lower resistance, it's going to get the lion's share of the current. And specifically, since the 20 ohm is 1/3 the resistance of the 60 ohms, the 30 and the 30, since the 20 is 1/3 the resistance, the 20 will get 3 times the current. So that's why he gets 0.15 amps, and the 60 gets only 0.05 amps.
Okay, cool.
Hey, any other questions or issues? While you guys think about any questions or issues, this is a message specifically for Isabella. Isabella, I see you're one of the people here. So BattleBots is called off. We're going to have the competition next year. So all of the time, energy, and effort you put in for it this year will benefit the students who end up doing this next year. So thank you, Isabella. Thank you very much.
No problem. Glad to do my part.
Yeah, you're just a link in the chain, Isabella. So any other questions or issues?
Can you do number 76 on the homework?
Number 76, the battery has an internal resistance? Sure. It would be my pleasure. Number 76. And who is this talking?
It's me, Rosary.
Rosary? Oh, Rosary, good. Okay, here we go. Because, yeah, my little screen isn't like, I don't know why, but it's not set up. When I'm screen sharing, when I'm, doing this iPad thing, then it is not conveniently telling me who's speaking. So what a stupid Zoom. Okay, here comes 76. A battery has an internal resistance, so they tell me the internal resistance. That kind of takes the fun out of it.
I'm on a conference call.
What's that? Oh, you were not talking to me.
Oh no.
Yeah, that happens when my wife walks through the room. So we've got a 9-volt battery with a 0.012 ohm internal resistance, which, by the way, that's an incredibly small internal resistance. When if we were to do the lab, which is a shame we don't get to do, but on the lab, you guys are going to find, you would have found that the internal resistance of your 6-volt batteries, 6-volt lantern batteries, range between like 0.4 ohms and 2 ohms. So the internal resistance of batteries is pretty significant. So 0.012, that's a very, very low internal resistance. Okay, so what is the maximum current that can be drawn from the battery without the terminal voltage dropping below 8.9 volts? Well, here's the thing. So this is your terminal voltage from there to there, and we designate the bottom voltage as 0 volts. So there's your terminal voltage, and they say they want this guy to be 8.9 volts and no less. Well, the only way you lose terminal voltage is for there to be a significant voltage drop across that 0.012 ohm resistor. And oops, oh my God, I lost it again. Oh, there's a little kitty. Oh, I got it back. Okay, so here's the thing. If I start off with 9 volts and then I want the terminal voltage to be 8.9 but no lower, that means that the most voltage drop I can get across that internal resistance is 0.1 volts. So is that okay with you, Rosary, that's got to be 0.1 volts and no more?
Yeah, you could say that I was confused on what EMF stood for.
Oh, what what stood for the EMF?
Yeah, EMF. Yeah.
Yeah, EMF is another synonym for voltage. We call it electromotive force. So yeah, it's weird, and I don't know enough to know why sometimes they use EMF and sometimes they use voltage and sometimes they use electric potential and sometimes they use potential, because to me as an engineer, they all mean the same thing. They just mean voltage, you know?
Oh, okay.
Yeah, so anyway, that's it. They're by saying the battery has an EMF of 9 volts, they're saying that the battery, is 9 volts if there's no voltage drop across the internal resistance of the battery.
Okay.
Yeah. Hey, any other questions or issues?
Is there a difference between the circle with the squiggle in it and the 2 lines?
Yes. I try to, this is physics 1, so we only work with DC voltage. We don't work with AC voltage, but actually your wall socket is AC. That is, it's sinusoidal. It's a voltage that's changing sinusoidally. So to show an AC, an alternating current, which means sinusoidal voltage, you do this. But if you've got a battery, which is DC voltage or direct current, then you do your battery like this. And also you'll do this, even though with AC, there's not really a positive and negative terminal of AC because it's sinusoidal. It's half the time it's positive, half the time it's negative, but definitely when you have your home wiring, one side is probably earth ground, so you really want to make sure which is the safe side and which is the incredibly dangerous side. But anyway, yeah, this is the difference between direct current voltage, or what we call DC voltage, which is like what batteries provide, and this is alternating current, or AC. So Cameron, is that the question you're asking?
Yeah, thank you.
Yeah, that's it. And of course, yeah, good. All right. Hey, any other questions or issues? All right, then, hey, kids, I think we're going to end our little meeting. So here, let me stop sharing. Boop. Okay, so who's left? Hey, we still got some of us left. Yay. And yeah, I'm going to end the meeting. So thanks, everybody. Thank you for coming. And as we approach the day of our Chapter 20 exam, you know, I'll start giving you more and more, you know, problems for you guys to do instead of having just me talking. And yeah, that's it. So have a good day, you guys.
Thank you, Mr. Shana.
Oh, you're welcome.
Thank
Thank
you.
you.
Yep,
Bye-bye.
thank you.
I'm ending the meeting now. Wait, end meeting.